Thank you.
You're welcome.
Well, good morning. Today's lecture finishes up the carbon matrix composites, and I have two case studies today. This first one is improved thermal shock resistance of magnesia graphite refractories. They're adding MgO carbon pellets to improve the thermal shock resistance. So these magnesia graphite refractories are usually 12 to 20 weight% carbon, and then the minor additives like the antioxidation agents. And these are used extensively in steelmaking, basic oxygen furnaces, ladles, electric arc furnaces. The main carbon source is typically flake graphite, has a little better oxidation resistance compared to amorphous carbon. And there's a stress concentration from the thermal anisotropy of graphite, and that mismatch creates microcracks. And the minor additives are usually metallic aluminum and silicon, and they form ceramic phases in the refractory, usually in conjunction with oxygen. They're oxygen getters. So they remove the oxygen before it can react with the carbon. So in this study, they replaced flake graphite with MgO carbon pellets in order to reduce the carbon content and improve the thermal shock resistance. So the carbon content in a commercially available MgO carbon composite in this study, the one they looked at was a 14 weight% flake graphite, and they tried to lower the carbon content with this granulated flake graphite in the form of these MgO carbon pellets to get the flake graphite content down from 14 to 10 weight%. The flake graphite is a costly component, so part of this effort was probably to reduce cost. So how they made the MgO carbon pellets, they started out with a fused magnesia powder, so dense porphyry powder. They used flake graphite and then the phenolic resin. And again, phenolic resin has about 50% carbon yield. So these were pressed into pellets. The resin was cured at 200 degrees C. It's very brittle at this point. And then it was crushed to a minus a half millimeter particle size. And they labeled it GP for graphite pellets. And then the actual samples, the MgO carbon samples, were made with, again, fused MgO, and the maximum size was 3 millimeters. Flake graphite, phenolic resin. They added the metallic aluminum and silicon as the antioxidation agents. And then GP, they added the MgO carbon pellets. So these were pressed into samples. Resin was cured at 200, and then they coked the samples at either 1,000 or 1,400 degrees C. And again, coking is just burying these samples in carbon in a sealed container and then heating them up to pyrolyze the resin, convert it to carbon. So there were 5 compositions here. They all had 70% fused MgO. They all had about 1% silicon metal, 2% aluminum metal, and then the resin between the powder and the liquid portion was 5%. So what they varied was the magnesia fine powder, the flake graphite, and then the amount of these pellets they created. So the combination of all these 3 was always 27%. So here they took out some of the magnesia powder, some of the flake graphite and added 4% of the MgOC pellets. And here, GP, that was GP2, GP5 had 10% of the pellets, GP10 had 20%, and G14 is basically duplicating a commercially available MgO carbon composite at 14 weight percent flake graphite. And this one had no level of the pellets, the MgO carbon pellets. So when you do the X-ray diffraction to look at the phases present, the triangles are MgO periclase, the stars are graphite. Those are the major components. The silicon metal and the aluminum metal, the diamond and the double circle. Here's some silicon metal. Here's some aluminum metal. They're showing up at the lower temperatures, and then they're converted to spinel, silicon carbide, and aluminum nitride at the highest temperature, 1400 degrees C. So you can see there's small amounts of aluminum nitride, silicon carbide, and spinel. The peaks are very small, but there's small amounts of those components. So this is the density and porosity after curing the resin and then coking at 1000 and 1400 degrees C. AP is apparent porosity, BD is bulk density in grams per cubic centimeter. So they have here G10, then GP2, GP5, and GP10. After curing the resin, the porosities are all 7 point something, so between 7 and 8. The bulk densities are very close to about 2.9. So adding the pellets didn't really affect the density. Then at 1000, the porosity goes up to around 12% for all of them. This one's 13. And that's because the weight loss during coking, where you pyrolyze the resin. And then the bulk density goes down a little bit because of the weight loss. And at the highest temperature for coking, 1400 degrees C, the bulk densities maybe go up slightly. The porosities maybe go down slightly because of some sintering processes taking place and densifying the material. So they measured 3-point bending for the strength. They measured a resonance technique for Young's modulus. They measured thermal expansion from room temperature to 1200 degrees C and in inert atmosphere nitrogen. And for the fracture surface energy, they used the work fracture test in 3-point bending, which is that chevron notch bend bar. So we've seen this formula, the work fracture equals the integral of PDX, the area under the load displacement curve, divided by 2A, and A is the area of the remaining triangle ligament. So this was the chevron notch. That's 3-point bending. The load is applied in the center, and then your 2 lower knife edges. W is the width of the sample, H is the height, and A is this area that's fractured. The thermal shock was done on the coke samples at 1400 C. 900 degrees C was the heating temperature, and then the quenching temperature was 20 degrees C. They ran 5 cycles and used the 3-point bending to monitor the damage. So this is the microstructure of G10. That's without any pellets without any MgO carbon pellets, cured at 200 degrees C. So FM is the fused magnesia grain. You can see that it's basically pore-free. It's very dense, fused cast. You can see on this coarse grain and this one, you can see the white areas. That's an impurity, uh, usually a calcium silicate. And that etches really shows up where the grain boundaries are. So this portion was probably a single crystal, and these were also single crystals, but these are crushed aggregates. So fused MgO, some impurities. The black regions are the flake graphite. And then there's a small spot here. That's an aluminum metallic particle. And then the other small spot here is a silicon metallic particle. And then this is the microstructure of the sample with GP5. So it had MgO carbon pellets. And these circled areas are the actual pellets. So you see some fine MgO particles, and then the rest is the resin graphite matrix that's been crushed. So the pellets show up and are outlined here. This is GP10 after curing at 200. So these regions here are the pellets in the matrix. And this is G10 after coking at 1,000 degrees C. So G10 again had no MgO carbon pellets. The X-ray diffraction picked up some spinel, MgAl2O4, and an aluminum carbide. So they're just pointing out where these minor phases are located. So they picked up some spinel and some aluminum carbide, and they're using EDS to figure out what the chemistries of these different features are. And if the chemistries match up to spinel or a carbide, they can identify it. This is GP5 after coking at 1,000 degrees C. And all these small crystals are spinel crystals, MgAl2O4, forming on MgO aggregates. And this is another one of GP5 after coking at 1,000 degrees C, showing the carbide, aluminum carbide formation. And then GP10, which had a higher content of these pellets, the MgO carbon pellets. This is cooked at 1,000. You can see the needle-like structure of the carbides more clearly here. And then these blocky type crystals are the spinels. And this is a G10 after coking at 1,400. Again, showing this spinel crystals forming on the surface of MgO aggregates. So G10 had no pellet additions, and a little bit higher magnification of G10 at 1,400, showing these aluminum nitride kind of whisker needle-shaped crystals forming. And then this one is GP5 after coking at 1,400. You can more clearly in this one see the needle or rod-like shaped aluminum nitride crystals. And then they're showing where these aluminum nitride crystals are on this one. This is GP5 after 1,400. And you can see these sort of, some of them are flake-like, some of them are needle-shaped. So these are aluminum nitride crystals. And then this one, GP10, after 1400, you can see a lot of these aluminum nitride crystals forming, sort of like whiskers or needle shapes. And then maybe this is the last one on the fracture surfaces, but this is GP10, 1400 degrees C, and you can clearly see aluminum nitride forming. So the spinel and the aluminum nitride are minor phases. So if you measure these on a mechanical test machine, you get the following type of force displacement curves. These are cured at 200. So you have GP2, GP5, GP10. These have the MgO carbon pellets, G10 doesn't. So they all exhibit this kind of behavior. It's a brittle fracture. You have linear behavior up till fracture and a rapid strength loss. So it's a brittle kind of material. That's what you would expect from the resin after curing. It's a brittle material. Then after you coke it at 1000 degrees C and you generate a stress strain curve or a load displacement curve, these all become nonlinear. And then the fractures tend to be stable. There's no rapid drop off in the load at a particular strain. They tend to be more stable. So now it's not really a brittle fracture anymore. It tends to be more ductile. And then the strain to failure becomes larger. These were about 0.5%, and these are reaching maybe closer to 0.8%. And then the load displacement curves at 1400 degrees C, material coked at 1400 degrees C. Again, you can see that they're non-linear, they're not as brittle, and they tend to be more ductile. G10 is still a little bit on the brittle side, but they have an increased strain to failure for the ones with the pellets, getting closer to 0.9%. So the higher the strain to failure, the better they can accommodate, the samples can accommodate the thermal shock damage, and the better the thermal shock resistance. So these are the properties after 200, 1000, and 1400 degrees C curing. The strength, the elastic modulus, and the worker fracture. So if you look at the strength at 200, or this is G10, no additional pellets, a GP2, GP5, and GP10. The strengths are all about the same, 19 megapascals. The elastic modulus is about the same, 49 gigapascals. And then the worker fracture, they're all pretty similar, about 250 plus or minus, maybe 20. So maybe 250 joules per meter squared. Then when you coke it at 1000, the strength drops. All of these drop to about 6 megapascals. The modulus drops to about 6 to 7 gigapascals. So you have a more porous material, so that's going to drop the strength in the modulus. And the worker fracture also drops, but there's a tendency to show an increasing worker fracture from left to right as you add more of the pellets. And when you coke it at a little bit higher temperature, 1400 degrees C, the strength starts to go up again, 9 to 10 MPa. The modulus goes up slightly, maybe around 9 GPa, gigapascals. because of the sintering effect. And then the worker fracture, it's still lower than at 200 degrees C, but it is increasing again from left to right as you add more of the pellets. So the thermal shock results in flexural strength and then residual flexural strength, the ratio, and then the different types of samples, the G10, and then the 4 with the MgO carbon pellets. So the green is the strength before thermal shock, the gray is the strength after, and then the red diamonds are the residual strength ratio. So usually the higher the residual strength, the better the thermal shock resistance. So GP10 had the highest residual strength. So the composite without any pellets, the strength was comparable to GP2, GP5, and GP10, but the damage after thermal shock was greater, so it had a lower strength after thermal shock. And you can see as you increase the pellet concentration, the residual strength goes up, the strength after thermal shocking goes up, and it kind of reaches a maximum somewhere in between GP5 and GP10, and then it starts falling off again a little bit. But all of the samples with pellets had a higher strength after thermal shock than the sample without the pellets, and they all had a higher residual strength ratio. So the addition of pellets certainly improved the thermal shock behavior. So G10 before thermal shock. So this is the sample without any pellets. These gray areas are the fused MgO grains. You can see some impurity here. The black areas are the flake graphite, and the flake graphite will bend and conform to the shape of the aggregates, the magnesium aggregates. So this is before thermal shock, and you can see the crystals of the fused cast MgO. There's no cracks in these crystals. And then after thermal shock, you can see all the damage in the crystals. You can see all the arrows are indicating cracks. So arrows that are indicating the cracks in the MgO aggregates. So they were thermally shocked. What you can't see is all the micro cracks in the matrix. So the matrix, especially at the interfaces between the carbon and the aggregates are also micro cracked. This is GP5 before thermal shock, and they're outlining 2 areas of the pellets. And again, there's no micro cracks in the MgO grains. You can see some of the impurity here along the grain boundary between 3 crystals. Here's some more impurity over here between this crystal and maybe 2 other crystals. And then this is GP5 after thermal shock. The arrows are again showing the microcrack that are present, but the density is really decreased. So there's some damage in the coarser aggregates. And then there's a microcracking in these pellets. So this is probably one of the reasons why the strength goes up after thermal shocking is because of the less damage in the coarser aggregates. This is a GP10 before thermal shock, and there's quite a few regions here where the pellets are located. And again, no micro cracks in the MgO aggregates. And then after thermal shocking, there's a couple aggregates that have some cracking, but most of the micro cracks are taking place in these areas where the pellets are located. So microstructures after thermal shock. While there's microcracks in the MgO aggregates and between the aggregates and the matrix, the highest density of microcracks in these MgO aggregates was in G10. And then as we went up in pellet content, the density of the microcracks in the MgO aggregates decreased. So the lowest density of microcracks in MgO was in GP10. So the microcracks are related to thermal stresses due to temperature gradients or thermal expansion mismatches. We talked about both of these at the beginning of the course. So these are thermal expansion coefficients from room temperature to 1,000 degrees C for the different components. This is the thermal expansion, linear thermal expansion for MgO, and it's pretty high, 13 to 15 times 10 to the minus 6 per degree C. A minor component, spinel, was 8.4, let's say, times 10 to the minus 6. Another minor component, aluminum nitride, is pretty low. It's a nitride, 4.5 times 10 to the minus 6. And the silicon carbide is also pretty low, 4.7 to about 5 times 10 to the minus 6. So the nitrides and carbides are about half of the spinel and about a third of the MgO. So there's thermal expansion mismatches. The MgO is the major phase, and so is the carbon. So carbon is in the form of flake graphite, which is anisotropic. So in the C-axis, where there's weak bonding, it's 28 times 10 to the minus 6. And in the A-axis, where there's strong covalent bonding, it's really low, 1.5 times 10 to the minus 6. So if you look at these thermal expansions, especially for MgO and graphite, you can see the mismatch leading to a lot of microcracking in the matrix. So this is the thermal expansion that they measured versus temperature. And G10 is perpendicular to the shaping direction. And that's the open circle. And then this is G10, solid circle, parallel to the shaping direction. So when you press this material, the flake graphite tends to align, and the material is no longer isotropic, it's anisotropic. So the solid circle is parallel to the shaping direction, and then the open circle is perpendicular to the shaping direction, and that open circle is down here. So even as a function of direction in this one material G10, you can see there's a difference between these two graphs. There's a gap between the solid circles and the open circles. Then when you add these pellets, which are the crushed flake graphite and the MgO, GP5, the triangle is perpendicular to the shaping direction. That's the open triangle, and the solid triangle is parallel. So the solid triangle is down here, the open triangle is over here. So that gap between the thermal expansion in the two directions is decreasing. And then finally, GP10, open triangle perpendicular to the shaping direction and a solid triangle parallel. They're basically on the same curve here. So the addition of these pellets of the crushed material decrease the anisotropy in these refractory bricks. So when you look at the coefficient of thermal expansion from room temperature to 1200 degrees C, this is parallel and perpendicular to the pressing direction. And then this is the ratio of the two. So G10 has the highest ratio, GP10 has the lowest ratio, and then GP5 is in between. So the addition of these pellets decreases the anisotropy, basically because they're crushing the large flakes of graphite into much smaller pieces. So in this material, as far as the microstructure is concerned, the addition of these MgO carbon pellets as a replacement to flake graphite improve the thermal shock resistance of the magnesia graphite refractories. It reduced the damage due to microcrack formation in the coarser MgO aggregates, and the damage that was allowed to take place was primarily in the matrix of the graphite and MgO interfaces, where the MgO particles are much finer. So as far as the test methods are concerned, the addition of MgO carbon pellets didn't really affect the strength of the MgO graphite materials. The addition of the pellets reduced the thermal expansion anisotropy, which helps control the damage, reduce the damage during thermal shock. The addition of the pellets also increased the work of fracture, and they increased the strain to failure. So by reducing the anisotropy, improving the work of fracture, improving the strain to failure, and maintaining a reasonable strength, they actually made a somewhat better MgO carbon refractory with a lower graphite content. So in terms of thermal shock, they actually improved the refractory, probably made I don't know how much savings they got from cutting out 4% graphite, but there should have been something. But then they have to make these pellets, so the graphite is actually crushed into these pellets. So there may not have been a big advantage in savings, but there was certainly an improvement in the thermal shock resistance. Cutting out the carbon is also detrimental to the corrosion resistance. So these composites are made to have improved thermal shock resistance and improved corrosion resistance. So when you sacrifice maybe carbon content and try to improve the thermal shock, you might sacrifice the corrosion resistance. This other work improved thermal shock resistance of low carbon aluminum oxide carbon refractories fabricated with carbon spinel composite powders. So they looked at the effect of additions of carbon spinel, and spinel is MgAl2O4, composite powders on the thermal shock resistance of alumina carbon refractories. So these are low carbon composites, and they're low carbon because they want to keep the carbon content low to prevent carbon pickup by molten steel. So these kinds of composites have good thermal shock resistance, and they're used in transferring molten metals. They're used in nozzles and tubes and slide gate plates, and keeping the carbon content as low as possible to prevent carbon pickup by the molten steel. But lowering the carbon content degrades the thermal shock behavior, and also degrades the corrosion resistance. So there's been a lot of work recently on nanoparticle additions to refractories. Everybody likes to do research on nanoparticles these days. So the problem with nanoparticles is they're expensive and they're hard to disperse because of the high surface area. But this composite here, carbon MgO composite powder, is a carbon nanoparticle in a spinel matrix. So some of the recent work on nanocarbon additions to refractories have shown that you can decrease the total carbon content and still improve the properties of these composite refractories. Nano carbon black has been used. Nano graphite has been used. Um, they all tend to improve the strain of failure, so they have high deformation for thermal stress relief. Nanocarbon fibers and tubes have also been used, and they enhance some of the toughening mechanisms like fiber pullout, crack bridging, crack deflection. The problem with nanocarbons, they have high cost. Um, if you're trying to make a refractory product that's low cost, that's going to be a big issue. And they're hard to process. They're hard to disperse because of the fine particle size and high surface area. So this paper is kind of eliminating some of these problems. They're providing a solution to incorporate nanocarbons into refractories and form these composite powders. So what this is, how this is made, they carbon spinel composite powders. They have an agglomerated microstructure, and they prepared these in a simple one-step method. So you start out with alumina, Al2O3, and a magnesium citrate trihydrate compound. So this is magnesium citrate trihydrate, C12, H10, Mg3O14, and then 3H2Os. So you have in this combination, you have your source of aluminum, your source of carbon, your source of magnesium, and you also have oxygen. So you have everything needed to make this composite powder. So this mixture is cooked at 1400 degrees C. And then the final product, what you end up is a multi-layer graphene. So graphene is one layer of carbon atoms. They're in the hexagonal rings, just like in graphite, but it's one atomic layer. But in this composite powder, it is multi-layer graphene, usually 6 to 10 graphene layers that are dispersed in this agglomerated mixture of graphene and spinel. And the carbon content from the graphene is about 8%. So you have this powder with nanoparticles of graphene dispersed in spinel with about 8% carbon. So these are the materials they looked at. They're all pressed. The resin was cured at 240 degrees C, and they were then cooked at 1400 degrees C. So it goes from AC0 to AC6, and then there's one with carbon black. This happens to be a nano carbon black edition at 0.36%. So the Al2O3 aggregate, of course, their aggregates were all in the 65% range. Metallic aluminum was 6%. Flake graphite was 2%. Fine particle size alumina, which is reactive alumina, 6%. They had B4C for an antioxidation agent at 0.6%. And then the phenolic resin was held at 4%. So they dropped the amount of finer aluminum oxide powder as they added the carbon spinel. So Ma is the magnesium aluminate spinel. So they added these powders from 1.5 to 6, and that's indicated on these different labels. So they dropped the aluminum powder and added this spinel powder in its place. And this last one had 0.36%. This is nano carbon black. And it actually has the same carbon content as AC 4.5. So if you take about 8% of this 4.5, you're going to end up with 0.36. So they put this one in just to look at the difference between a nano carbon black and a nano graphene that's in these aggregates of basically spinel. So AC 4.5 and CB 036 have the same carbon content. So when it's cooked at 1400 degrees C, you have different kind of reactants that are present. You have aluminum, aluminum oxide, carbon, nitrogen, oxygen. And coking is basically burying the samples in a crucible filled with coke, closing it with a lid and heating it to uh, heat treat these things in non-oxidizing conditions. So these are possible reactions that can take place. Um, Al plus nitrogen forming aluminum nitride, Al plus carbon forming an aluminum carbide, Al4C3, aluminum plus carbon plus oxygen forming an aluminum oxycarbide, Al2OC, and then Al4C3 from this reaction plus Al2O3, again forming this aluminum oxycarbide, Al2OC. They put down the Gibbs free energy change for all of these reactions. And if you plug in 1400 degrees C for T, the temperature in any of these equations, you get a negative delta G. So that just is showing a negative free energy means the reaction will proceed from left to right. The X-ray diffraction shows AC 0, AC 1.5, AC 3, AC 4.5, and AC 6. So they're going up in the carbon spinel powder additions. So the stars are corundum or alumina. That content is high in all of these. The diamond is graphite. It's present again in all of these, but it's a lower percentage. And then the minor phases, but these two are forming aluminum nitride and aluminum oxycarbide. The solid circle and the stars, open stars, they're forming in trace amounts. And then your inverted open triangle is the spinel powder addition, and you can see it's there, and all of these except this one, AC 0. So they measured 3-point bending strength at room temperature, 3-point bending strength at 1400 degrees C, so it's a hot modulus of rupture, and compressive strength at room temperature. The bend bars are typical sizes, 25 by 25 by 140 millimeters. The strength is measured on a cylinder, the compressive strength, 50 millimeters in diameter, and then 50 millimeters high. So the bars that were coked at 1400 degrees C, the 25 by 25 by 140 millimeter bars were thermal shocked. They were quenched from 1100 degrees C to 20 degrees C in water, subjected to 3 quenching cycles, and then 3-point bending was monitoring the damage to 3-point bend strength. They also looked at oxidation resistance and corrosion resistance. So again, carbon matrix composites are designed for good thermal shock resistance and good corrosion resistance. Oxidation resistance is always an issue. Once you oxidize the carbon, you no longer have a composite. So they measured the oxidation resistance on these cylinders. Like again, they're 50 millimeters in diameter, 50 millimeters high, and they use the same size cylinder to measure the corrosion resistance. So This is a qualitative measurement they did. They heat treated these cylinders in air for 3 hours at 1400 degrees C. And then they cross-sectioned the cylinders in the horizontal direction and measured the decarbonization zone, the thickness of that layer. There's other ways to measure oxidation resistance, like thermogravimetric analysis, where you get a quantitative number. And the corrosion resistance is also qualitative. They took these cylinders, they drilled a hole 20 millimeters in diameter, 18 millimeters deep, and they filled that hole with 10 grams of slag, and they heat treated those cylinders with the slag in the air at 1650 degrees C, 3 hours. And then they made a vertical cut and examined the slag penetration depth. So they use a basic slag, so it's high in lime and MgO, almost 50%, the balance being silica and iron oxide, about 10% silica and about 35% iron oxide and 50% combination of lime and MgO. So it's a very basic slag, which should work just fine in combination with aluminum oxide, because aluminum oxide is neutral. So you can put a basic slag in contact with a neutral refractory like Al2O3 or a basic refractory like MgO. So going from Ag0 to AC6, the apparent porosities are all between basically 14 and 15. The bulk densities in grams per cubic centimeter are all just a little higher than 3. So there was no real difference in porosity and density on these materials. And when they measured the strengths here, it's going from Ca0 to Ca6. So they're increasing the amount of the carbon spinel powders. The solid squares are the cold MOR, the blue triangles are the hot MOR, and the red circles are the cold crushing. There's a break in the curve here because these materials are always much stronger in compression than in bending, which is basically a tensile failure. So there's a tendency for any of these strengths to decrease with the additions of the carbon spinel composite powders. So they attributed that to microcrack formation due to thermal expansion mismatch between the matrix and then these composite powders. And interesting, the hot strength is higher than the cold strength, and they attributed that to stress relief at high temperatures. So the blue triangles are slightly higher in strength than the black squares. So the strength in bending before and after thermal shocking, we have our load displacement curves. And the right-hand side is before thermal shocking. So it's pretty linear up until failure with a rapid drop in strength. That's a brittle fracture. But the materials after thermal shock, they were non-linear and stable type fractures after the crack started to propagate. So these are more ductile or less brittle after thermal shocking. And then before and after thermal shocking, these are the bending strengths. So cold MOR, and then residual strength ratios. So this turquoise color is the MOR before shocking, and the purple is after shocking. So AC0, the highest strength, and then as you added more of these carbon spinel powders, the strength started to fall off, and they theorized that the microcracking, when you added this powder, lowered the strength. But oddly enough, the residual strengths, the strengths after thermal shocking, go up with the carbon spinel powder additions. So they're a little bit better than these materials without the powder additions. And if you have a lower strength to start out with and a higher strength, afterwards the residual strength ratio goes up. So if you're looking at residual strength ratios, this material, AC 4.5, is what would be rated the best in terms of thermal shock. So any of these materials with the addition of the carbon spinel powders appear to have a better thermal shock resistance than without. So this is the microstructure of the material without any composite powders. There's not much to see here. It's pretty dense as formed, and you can see some black spots, some porosity. And this is the microstructure of the material with 4.5% graphene carbon spinel additions. There's some porosity present. So if you look at the microstructure here, this is the material AC0, no composite powder additions. You can see one of the pores here. We're looking at a higher magnification. Not much that happens here on the surfaces. There's some ceramic phases are generated, but it's not generated to a great extent. And this is just a higher magnification of AC0. You can see some particulates forming. So there's some phases are starting to form in the pores. It's actually forming everywhere in the microstructure, but you can see them more easily on the pores. This is AC 4.5. They're looking at the pores again, and there's more ceramic phases forming at those surfaces. And this is a higher magnification of an internal pore. And then they're starting to see these rod-like structures that are forming in the microstructure. And then this is an even higher magnification of AC 4.5. And you can clearly see the rod-like structures that are being formed in these materials. And just another even higher magnification of the same rod-like structures in the pores. You can see they're forming. So this is the before and after strengths for thermal shocking of AC 4.5, which we said had the optimum behavior for thermal shock, against this one, CV 0.36. So this has no carbon spinel powder additions, but it has the nanocarbon black addition at 0.3%, 0.36%. And if you look at the residual strengths here, the AC 4.5 had a better residual strength retention. So when you added these composite powders, they produced a more tortuous crack path. So even though these carbon contents are exactly the same, the graphene carbon, the nanographene carbon incorporated in the spinel created a more tortuous crack path and improved the thermal shock resistance slightly over this one with just the carbon black. So they're saying there was enhanced thermal shock resistance with the composite powder additions, producing more tortuous crack paths. So this is AC 4.5 again after thermal shocking. And this is one of those aggregates where you have the graphene carbon layers in the spinel. And then they're highlighting this area here where the crack is branching, it's branching again and again. So it's a more tortuous cracking type path. This is just another example of AC 4.5 after thermal shocking. And they're showing this area enhanced over here. The crack is branching, and then it's continuing to branch all along this path. So these composite powders are creating more tortuous crack paths. So this is an area of one of those powders. So this is a graphene carbon spinel powder outlined here. And this is before thermal shocking, and then this is after thermal shocking. So they're saying, well, these areas, these powders that contain the graphene, these composite powders are consuming more of the stored elastic strain energy by fracturing. So they're fracturing internally, dissipating stored elastic strain energy. And then they're also looking at the rod-like structures that are forming around these powders, these composite powders. So you can sort of see the different rod-shaped powders in this crack here, and then here's a higher magnification of some of the rod-like shapes in a crack. And then this is much higher magnification of this rod-like structure in bridging in a crack. So I mentioned there's other studies of what they call novel carbon additions. These are nanocarbon additions to other refractory systems, and they're all saying, well, they're beneficial in terms of improving the thermal shock resistance. So here was an MgO carbon system with 5 weight percent graphite flakes, and then this is an MgO carbon with 4.5. And some of the additional carbon is in the form of nano sheets of carbon. And then when they look at the residual strength ratios, there's some improvement from 41 to 37. And this one is with an expanded nanographite, an expanded structure. Again, just a slight increase. And then here's some additional aluminum carbon composites. These had 3 weight percent plate graphite. And the second one here was reinforced with a multi-walled carbon nanotube. And there's a substantial increase in the residual strength from 37 to 76%. And then this one had some, again, multi-wall nanocarbon tubes. And this one really did not show a great advantage. But the last one here is the one we just looked at, the aluminum oxide carbon composite with these graphene spinel powders, and their residual carbon, the residual strength was about 45%. So in some cases, nanoparticle additions, depending on what they are, have actually improved the thermal shock resistance. So other people are researching this and recently, or have researched it recently. And again, the problem with using nanocarbon particles of any shape is that they're expensive and hard to work with. But this approach here, where you form the graphene carbon in situ in the spinel material is a much easier way to do it. Probably lot less expensive. So I mentioned they measure oxidation resistance and corrosion resistance. So these are the cylinders that were oxidized in an air environment. These are the cross sections. So the cylinders are cut. The white areas are where the carbon has been oxidized, the decarburized zone. And then the black area is the remaining carbon. So they're kind of circled in red there. They're all, in my opinion, pretty much the same. So as you go from no composite powder addition to AC6, which I think was 12%, there's really no difference in the oxidation. So this is a plot of the decarbonization layer in millimeters versus the 5 different compositions. And they're all around 9 to 10%, 8 to 9, 10%. There's not a great deal of difference in the oxidation. But apparently there was a significant difference in the corrosion resistance. So these are the vertical cross sections of the cylinders. So you can see where the hole was in the top of each of the cylinders. That's where the slag was placed. So this was done in an air environment. So you see a decarburized zone around all of these cylinders, and the black area is the remaining carbon that's not been oxidized. And then this darker gray area, gray yellow type area outlined with this dotted line is the slag penetration. So the slag penetrates a bit more in these refractories after they've been decarburized compared to these materials with a higher powder addition, composite powder addition. And if you measure the corrosion depth, there's a significant improvement with these composite powders. So a lot less corrosion. So they are also affecting the corrosion resistance in a positive manner. So in this experiment, the addition of these graphene, carbon, spinel composite powders promoted the formation of microcracks. And this is an agglomerated type microstructure that decreased the stored elastic strain energy. The addition of these composite powders also promoted this rod-like ceramic fiber formation, and they attributed increase in thermal shock resistance because of fiber bridging. In terms of the test methods, the composite powders improve the thermal shock resistance, and the composite powders also enhance the corrosion resistance. So that's what I have today. 2 types of carbon composites, one an MgO carbon, one an aluminum carbon, 2 different approaches to adding these agglomerates, these pre-reacted powders to improve the thermal shock resistance. And the second one is based on nanotechnology. So I don't know how long it's going to ever take these to go into production. Well, maybe never, but we'll see what happens in the future. So that's what I have. The last class is next Tuesday. I'll have some papers on monolithic refractories, castable refractories. So again, thanks for listening today, and I'll see you next Tuesday, and have a good weekend in between. Thank you.
Thank you.
Thanks.
Okay, so we'll be probably be Greg next week, okay?